Okay, it looks like we're recording and everything's good. So here's where we were last time. By the way, I hope everybody had a good, depending on your class schedule, possibly 4-day weekend. I had a 4-day weekend effectively because I only teach Monday, Wednesday, Friday. So anyway, so here's where we were. We were talking about the cross product. We've already talked about various properties of determinant, which you may or may not have seen before, and we talked about this idea of right-hand order and left-hand order and such. Okay. All right, so the cross product, now again, reminder, it's defined with this kind of weird-looking formula that I don't think most people memorize because there's this much easier formula right here, which admittedly a little sketchy. I mean, it says determinant. You're supposed to take the determinant of matrices. Matrices are supposed to have elements that are numbers. These elements up here, elements that I'm calling, as if this makes sense, are vectors, not numbers. So that is weird, but if you ignore that and just follow the symbolic formula for determinant and just kind of write it out, it gives you exactly what you're supposed to, right? So this is a wonderful little shortcut convenience memory tool, or whatever you want to say there. Okay, this is where we finished last time. So moving along, now with this still up on the page, I'm going to point out that some really nice stuff happens when you look at this. Oh, this little construction here. It's a dot product with a cross product. This is called a triple product. This specific construction, this specific arrangement. And the reason it's neat is because if you just take the formula for the cross product here, right, and then you dot out, dot it with a C vector, like so, and you can just write down what it is. And pretty quickly, what you notice is that this formula here is just reproducing pretty much the structure of a determinant. So in particular, notice we've got C1 times that little expression. But yeah, here's C1, and this other little expression is the determinant of that minor. Right? So, and then et cetera on down the line. And so anyway, wonderful little fact then, this triple product construction, here it is, the triple product, is a determinant. So pretty neat fact. A little bit of a weird fact, you might say. Let me explain why this is an important fact to know. It's an important fact to know because we're trying to learn about the cross product. That's our sort of brand new shiny toy we want to play with and figure out how it works. Well, apparently, this formula relates that cross product we're trying to understand to a dot product that we already understand pretty well, and a determinant which we already understand pretty well, right? So that's broadly speaking, how you learn about new things is you relate them to old things that you already understand. So a very important formula for that reason. All right. So various facts that I need to show you now. Now, I'm going to remind you, as I said last time, 5 days ago, I guess it was, there are a bunch of proofs in the notes here and in the book that you are excused from. You're not responsible for those proofs. We just don't have time, tough choices, and all of that. But again, this is a tough choice where if I don't cover it, I feel like this is challenging enough that I also shouldn't make you responsible for it. So you don't have to read these proofs, but I'm going to remind you again as well. I hope you will. They're pretty neat, and it's good practice. It's good sort of experience in working with these various tools, and therefore an opportunity to get more intuition and understanding of the tools that you are responsible for. So give them a look. I encourage. I'm just going to rattle off a bunch of theorems. First, cross product is orthogonal to both of the input vectors, both A and B. Now you can prove this various different ways. And again, I'm not going to go through these proofs other than maybe a very broad stroke here. But one, if you want to show that something is orthogonal, orthogonal means compute a dot product and show you get 0. So, I mean, this is a plug-in chunk. If you want to just directly write down the formulas for these dot products, sure enough, they're 0. I'm going to point out that that's cryptic, though. I mean, it's so that removes all doubt. It proves it in the sense of it gives us certainty in the conclusion, but it doesn't help us really get any sense or intuition or satisfaction, one could argue. I like to say it, perhaps a little bit of an abuse of terminology here, but I like to say this shows that this theorem is true, but it doesn't explain why it should be true. You know what I mean? So for that, I'm going to point you toward this argument down here, which says bring in the triple product. And now keep in mind, the triple product involves a cross product. There it is. But it also involves a dot product, and we know that a dot product being 0 means something, so there's our knowledge of the dot product being useful. And we can relate that to a triple product. Relate that triple product to a determinant. We already know determinants relate to volumes, and one could make an argument about this volume just purely geometrically. Right? So now details. Take a look. That's actually most of the ideas right there. But the punchline here is the triple product formula has allowed us to connect cross product to things we already understand, and you can make the case that this picture right here, right, of a kind of a parallelepiped, but where two of the vectors are the same, right, arguably is directly connected by the algebra to this picture of vectors being perpendicular to each other. So I think that's lovely. It's a really nice opportunity, again, for geometric intuition and satisfaction. Okay. Another weird fact. The triple product cycles. So remember, by cycling, what I mean is, let's see here. I wanted to go to pencil mode. If you sort of move everything over by 1, and then when it falls off the side, you go back over to where you'd started. Cycling does not change the triple product, which is weird when you think about it as a statement involving dot products and cross products. And what used to always creep me out about this is, for example, in this construction right here, A is not part of the cross product. But in this construction over here, A is part of the cross product. So this is not some simple fact, it's like, distributivity or something. This is not, I've seen this a million times before. This is something really significantly different than just a basic, boring old rehash of algebra, right? So now again, different ways that you can prove this. Give these comments down here a look. These are nice exercises to help you, again, get more sort of familiarity and intuition and sense for how these things work. But very important to know, triple product cycles. Okay, here's a weird one and question. Yeah.
Is the order important?
The order is important, yeah. So notice I didn't say equals ... right? So it's just specifically these 3 of the 6 different possible ways to arrange A, B, and C. Just these 3 are equal. In particular, it is cycling specifically that preserves the triple product. If you just jumble them, that may or may not be a cycle. Is that cool? Yeah. Everybody happy? Okay. Next one. Again, kind of a weird one. And a wonderful proof. And again, I'm not going to go through it. Love to. I'm going to restrain myself, though. The magnitude of a cross product is equal to, and by the way, here it is, that magnitude of this cross product between A and B is equal to the area of the parallelogram defined by the 2 vectors A and B. So this length is equal to that area. weird fact. Yes.
So the two lines, that means.
Thank you. This is a notation that I have to admit I don't remember. I may have seen this before, but one way or the other, I like this notation, and I'm trying to popularize it. Two parallel lines followed by a list of vectors. I just mean the parallel thing that's defined by these two vectors. Yeah. In this case, parallelogram. Down here, you'll notice I have the same kind of notation, but followed by three vectors. That's a reference to this parallelepiped. Yeah. So just very simple, streamlined, I think pretty natural notation. Yeah. Okay, so again, not going to go through the fact, but it's a really cool proof, and I hope you'll give it a look. The punchline, though, is very important. Make sure you know that cross-product magnitude is the area of the parallelogram. Okay. Here's a weird one. We've talked about what it means when a dot product is 0, orthogonality, maybe even perpendicularity and all that. What does it mean when a cross product is 0? And it turns out it just means that that pair of vectors is linearly dependent. And again, there's a cool argument here. The cool argument is very simple. There's simple case arguments that you can make to connect both of these statements to a common shared sort of easily reachable statement about the area of a parallelogram. Give it a look, think about it, draw some pictures. Again, not responsible for the proof though, but it's a nice exercise. Okay. Here's a good one. This list, and I emphasize order matters, right? So this is A comma B comma the cross product of A and B. I'm putting the cross product third. Furthermore, this third vector, the left entry in the cross product, is the first vector listed. The right entry into the cross product is the second vector listed. All that matters. Right? That list is never in left-hand order. Now, most of the time, people are just ever so slightly sloppy about this and say that this list is always in right-hand order. And of course, it's possible one of the vectors could be 0, or two of the vectors could be parallel, or something like that, right? So we can't technically say it's always in right-hand order, but it is never in left-hand order. And again, cool proof. Again, give it a look. I encourage. Don't have to, but I think it's a nice argument. Okay. How we doing? Everybody all right? By the way, here's another cool fact. If you look at and I didn't write this down, and this is, you don't have to know this, but I think it's a nice exercise. It's going to actually also call up some of your old linear algebra experiences from whenever you took linear algebra. This list of vectors, if you look at the span of that trio of vectors, it's never two-dimensional. It could be three-dimensional, because there's three of them. It could be three-dimensional, it could be one-dimensional, it could be zero-dimensional, depending on what's parallel and what's, whatever. But that list will never be two-dimensional in span. So, nice fun little game to play. Again, good exercise if you're looking for a good exercise. All right. Is everybody on board? Everybody good? Okay, so recall I defined cross product with a formula. Very algebraic formula. It's literally, I just wrote down a bunch of expressions. Okay. What we have now is a purely geometric characterization of the cross product. And by the way, also perfectly satisfactory as a definition. Now, I didn't make this a definition, right? But the book does. The book starts with this geometric description of the cross product and then derives the formula that I started with. I start with the formula and then derive the geometric description. And there's many other ways than that to treat this material, and I've already given you all that little speech. And again, pros and cons. The books The downside of the book's approach is that there's just a bunch of algebra in it, and it's pretty nasty. And if you don't believe me, give it a look. I think you'll agree. Okay. So anyway, what is this geometric description? The cross product is the unique vector that satisfies these conditions. It's the unique vector, in other words, that is orthogonal to the two inputs, whose magnitude gives you the area of the corresponding parallelogram, and that makes this list not left-handed. There will always be exactly one vector that will do that.
Yeah, does it have to satisfy all three conditions?
Yes.
To be the cross product, or if they satisfy one, it is alright. Yeah.
No. These are not equivalent conditions. These are the cross product will always satisfy all of these, and only if a vector satisfies all of these can you know it's the cross product.
Okay.
Yeah.
So can you give an example one, for example, it satisfies the first condition, but it's not a cross product?
Oh, yeah, sure. So there's a whole bunch of vectors that are, like if this is A and this is B, right, then maybe the cross product of A and B might be that vector, right? But there's a bazillion other vectors that are also perpendicular to A and B that are not the cross product. Yeah, sure. Okay. All right. Again, different way to go. More facts about the cross product. It's not commutative. This is an uncomfortable one from an algebraic standpoint because we're so accustomed that stuff commutes, right? X times y is equal to y times x. I mean, we've been simplifying algebra since we were, whatever age that is, and just have gotten this extremely sort of accustomed to being able to just kind of move factors around however you want. It doesn't matter, right? 3 times 2 is 2 times 3. Who cares, right? You can't do that with cross products. It, again, just doesn't work. In particular, there's a minus sign that will go wrong, and so not commutative. Now, however, there is something still pretty cool about this equation. You don't have to view this as entirely bad news. It's also kind of good news, because it's not just that A cross B and B cross A are different. It's that they are always exact negatives of each other, right? So this is just a different kind of a cool fact. It's vaguely connected to commutativity. It's not commutativity, but it's still not all bad. Okay. All right. Now, some other facts, and if I recall correctly, these aren't in the book, but I think these are worth noting. Again, we talked previously about the idea that set up in a certain way, you can view cross product as being a function. Right? You fix some input vector A, that gives a function that acts on x just by crossing with x. And this function is linear. So we've made that observation before. I just want to write out now, sort of in full gory detail, what is that actually saying. And just keep in mind, cross product with A is what T is. Right? And so notice this equation that I have up here, just in fact directly it says that when you put a linear combination into T, you get the same linear combination out of T. All righty. And that, by the way, it's works on both sides. Here we had the excuse me, the constant vector A on the left. It also works if you do it on the right. The notation's a little bit weirder, but it's morally equivalent. Again, not the same. It's not commutative, but pretty easy argument to connect these. Okay. All right.
But shouldn't it be negative on one?
No, because there's negatives on both sides in some sense, and they kind of effectively cancel. Yeah, if you carefully write it all down, it works. Effectively, when you take this and kind of move things around, you get a minus sign there, and there, and there, and then you just cancel the minus signs. Yeah. All right. Okay. Another fact, just as more of a landmine observation, but don't make the mistake, again, of playing a little too fast and loose with the algebra based on all that experience of how awesome the algebra of real numbers is. So there's so many things that just work out, right? And distributivity, commutativity, right? And associativity. And that's another disappointment of cross products. Cross products not associative. You can't just move parentheses around. It just doesn't work. And it's not hard to convince yourself. You can write down some kind of random-ish vectors, and you'll just find that it just straight up doesn't work. All right. Okay, so bunch of facts to know about cross products, and just FYI, I don't want to get into the details here. Again, time being a factor and all that, but to the question of why do we care? Why do we have to learn about cross product? What a weird construction. How does that relate to me? Right? And so just a couple of examples of how cross product shows up in physics, and specifically torque. This thing called torque, which describes not how hard are you pushing something, but how hard are you turning something. Like if you're trying to get the bolts frozen onto with the nuts frozen onto the bolt, and you're trying to use a torque wrench or whatever to get that off of there. How hard do you have to turn? This is called torque, and it's a cross product, as it turns out. And then let's see here. Here's another one. It's about magnetic fields. This is a weird one. Don't blame me. I didn't make magnetic fields work this way. Right? They're very strange. But if you have a magnetic field, such as like so, and if you have a charged particle that's moving with a given velocity v through the magnetic field. Weird fact. The world that we live in is constructed in a strange way where movement through a magnetic field like so will create a force. And the formula for the force is a cross product. So that, again, this is ultimately a very natural thing. And physics is chock full of instances of the cross product coming up. All right. Okay, so moving along. Section 1.5. Now we're going to talk about lines and planes and such. We've touched on that a little bit already, but we're going to give a more full discussion. We'll start with the equation for a plane. So suppose you have a plane, some plane P. You want to write down an equation for that plane P. Well, we're going to need to know something specific about this plane. I can't just say, well, that one over there, right? I need to know this is the plane that goes through a particular point x naught, and that is perpendicular to what we call a normal vector n. And I appeal to your geometric intuition. Once you know a normal vector, right, that kind of tells you how the plane is oriented in space. Once you know that normal vector, the plane's got to be oriented a certain way. And then once you know a point that it goes through, that nails down what plane it is that we're talking about. Okay. So, given x naught and n, how would I write the equation of the plane? Now let me remind you what an equation is. An equation is a point tester. Right? So I need to figure out if I've got some point x and I want to decide if that point is or is not in this plane, how would I identify whether that point is or is not in the plane? And the big idea is that if it is, then this difference, x minus x naught, if you think about it, we know x naught's in the plane. That was given. we're assuming momentarily that x is in the plane, and that means that this difference is parallel to the plane. And if it's parallel to the plane, then that means that the dot product here, perpendicular vector dot parallel vector, must be 0. And wonderfully, this is an equation, right? You can tell from the equal sign right there. So, neat fact, by the way, that this interpretation about orthogonality relating to dot products is a fantastic connection between geometry. Right, we were making a geometric case about, well, if it's parallel to this, then it's got to be perpendicular to that. This purely geometric case, and we can translate that into algebra by way of this property of dot products. So cool fact. And there's our conclusion for the equation. Let me declutter here now for a second. Well, I'll just do it like this. That orthogonality gives us this dot product, which gives us this equation. And by the way, I slightly prefer this one. I don't know why. I guess I just kind of like the symmetry of how it looks, maybe. But these two equations are totally equivalent. Take your pick. It doesn't matter. All right. So this normal vector n, now keep in mind that normal vector, it's a vector. So it's got coordinates, and let's say for the moment that it has coordinates A, B, and C. And this point that we're trying to test, well, it's got coordinates. Typically we call them X, Y, and Z. So notice this dot product on the left, you can rewrite it as AX plus BY plus CZ. That's literally a dot product. And of course, this thing on the right now is just some constant. I mean, after all, we were given x naught, and I can just straight up multiply them out, and that is some number, D. So another alternative form of this equation, let's see, I'll keep my colors consistent, is to write down AX plus BY plus CZ equals D. And depending on the circumstance, this can be very convenient to write it in sort of a coordinate form. Right? It may come to you in a coordinate form, or for whatever reason you may need to rewrite it in coordinate form. So both of these forms are important to understand the role of vectors in the story. This one up here is much better. Because you can see the vectors, you can see that there's a dot product, you can see what x naught does, for example. Much better, all that's kind of cryptic in this form. On the other hand, I don't think I need to persuade y'all that writing out an equation in coordinates is also useful sometimes. I think that's more obvious. The big thing to remember here is that when you are relating these two forms, these two equations, ABC, the coefficients on the left side, when you write down an equation in this form, those coefficients are your normal vector. Really easy fact, yes?
Is the D always 0 since like n and x are perpendicular?
N and x naught are not perpendicular. It's n and x minus x naught that are orthogonal. Yeah, that's right. So x naught, probably not. Yeah. So yeah, D is just going to be some value. Yeah, right. Cool. All right. So here's an example. Suppose you know a plane by way of the following information. You're told these points A, B, and C. A, B, and C characterize a plane, right? You give me these 3 points. There's only one plane that can possibly go through all 3 of them. Right? What's the equation of this plane? Right? How do I figure out how to write the equation? This is a great example, sort of starter example of what I'm going to call a puzzle. And there's a bunch of these kinds of puzzles when you're dealing with lines and planes and stuff like this. I have certain information, but I want certain other information. And so the puzzle aspect of this is, look, I have certain information. I have a starting point, I have an ending point, and I have certain tools that allow me to do certain things. So how can I use those tools to get from what I have to what I want? And it's literally just a little puzzle. There are countless such puzzles. I couldn't begin to show you all of them, right? What I'm going to give you is sort of just a general strategy and a few examples. And the general strategy is just make sure to be very clear in your picture of what it is that you have. And then try to think backwards from what you want. And if you sort of move forward from what you have and backwards from what you want, you might find yourself able to meet in the middle. So broad stroke, that's how I think about this. So let's see here. What do we want? We want the equation of the plane. Okay. Working backwards, I want the equation of the plane. What gives me the equation of the plane? Apparently, I'm going to need to know a normal vector. Okay, so how can I use these 3 points to make a normal vector? Not clear. Okay, well now, okay, fine. Now let's work forward from what we have. I have these points in the plane. What can I possibly do with these points in the plane to give me anything of relevance? What can I make out of this? And, okay, here's one. If you have 2 points in a plane, notice that their difference is always parallel to the plane. Likewise, these other 2 points, A and B, their difference parallel to the plane. Okay, so previously, I had 3 points and I wanted to find an equation. Now, by sort of working backwards from my endpoint, working forwards from my starting point, now I have 2 parallel vectors and I want a perpendicular vector. And this is a connection that we can just directly see. We have something for that. That is the cross product, right? The normal vector that I want, the parallel vectors that I have, the cross product, makes that connection. Everybody with me? So again, the specifics of this example, are not the point here. It's not like you're going to encounter so many times in your future careers. Well, I've got the 3 points. How do I find that equation of the plane? Right. That's not the takeaway here. The takeaway is we were given some geometric information. We wanted some different information, and we managed to kind of connect the dots. Yes.
Does it matter if you do B minus C or like C minus D?
It's a great question. Yeah. That will give you, if you switch the order, then your normal vector will go the other way. And a lot of people say, ooh, well, wouldn't that change the equation? The problem, well, actually, the reason that's not a problem is because that extra minus sign that you get would be a minus sign on both sides of the equation. And when you have a minus sign on both sides of the equation, they cancel. So yeah, it doesn't. You'll get a different looking equation, but it'll be mathematically equivalent. Yeah, great question. Everybody good? All right. Okay. Here's a cool fact. This comes up more often than you would expect, and it's so easy to use. Once you know this fact, it's just super easy to use. So here it is. If you have no y's in an equation for a plane, there's just no y's there, right? So specifically, see, there's no y's in this equation. 0 y. That plane is parallel to the y-axis. So easy proof, and I'll go through that in a second, but notice how easy it is to use this. All you have to do is glance at your equation of your plane. Quick glance. Oh, there aren't any y's in there. Boom. Instantaneous, free, useful geometric information. Oh, this plane is parallel to the y-axis. right? It doesn't cost you any. You don't have to compute something to see if you get a geometric conclusion. You just at a glance get a geometric conclusion. So now why is this true? Pretty straight observation. Keep in mind we've already observed that these coefficients give you your normal vector. My normal vector then, something like this, coordinates A, 0, and C, and it's pretty easy to see that this is perpendicular to the y-axis, because after all, this vector, for example, that I've drawn here, parallel to the y-axis, 0, 1, 0, easy dot product. Dot product is clearly 0. That means orthogonal, which means as long as everything is null zeros, that means that this is perpendicular. So that's right. So this green vector is perpendicular to the y-axis. But of course, the green vector being the normal is perpendicular to the plane. So let's put it all together then. The plane is perpendicular to n. N is perpendicular to this purple vector in the direction of the y-axis. And now geometric appeal, that means the plane has to be parallel to the y-axis. Everybody buy it? Okay. Neat fact. By the way, now I've stated this with respect to the y-axis and y's in the equation. I'll bet you could probably speculate and prove your own similar results about x and z. And that's a good one to think through, and it's not very analogous, but it's a nice little practice exercise, so something to think about. All right. Okay, here's another puzzle. I want to parameterize a line where I am given certain bits of information. So I am given this point A that the line needs to go through, and I also am given that the line I'm interested in has to be parallel to both of these planes, like so. Right? So given two planes, they're going to intersect. They're going to define a direction by what their direction of their intersection is. I want to find the line that's parallel to that intersection direction, but also that goes through this other point, A. So how am I going to fit the pieces together? And again, think about what you have. Think about what you want. Ultimately, when I have the equations of two planes, notice that these coefficients give me my normal vectors. So that normal vector in 1, again, I can just read straight off of the equation, and this here in 2, I can read straight off of the equation. So yeah, I was given planes, but I'm going to work forward from that and further. I'm actually given a couple of vectors about which I know geometric information. What do I want? I want a parameterization. Well, if you think about it, what that means is I need a direction vector. I need something that I can use to define this direction, which combined with this A will allow me to write down a parameterization. So again, I was given some algebra. I want other algebra, but thinking geometrically, I was kind of given two vectors, and I want this other vector. And again, you can look at the picture and think about the geometry of the picture and persuade yourself that, yeah, again, the cross product is the perfect tool for this. The cross product is what allows me to take those two normal vectors and get this parallel vector, and then I win. Everybody okay there? Okay. All right. Now, I have, in both of the last two examples, I have used some geometric intuition about, well, this is parallel to that, and that's parallel to the other, and so therefore, and this kind of geometric intuition that's just unavoidably useful. I suppose it might be possible to write down all of these, what I like to call transitivities. This is parallel to that, and that's parallel to the other. Then the original must be parallel to the final. statements of that sort. But it depends on whether the things you're talking about are vectors or lines or planes or what. And whether you're talking about, does parallel and parallel imply parallel, or does perpendicular and perpendicular imply perpendicular? How does which of these many facts that I could write down are actually true? And rather than enumerate all of them, let me just point out a few instances where they don't work. And then the policy in this course is going to be use your geometric intuition and just heads up for the landmines, think it through, make sure that your geometric intuition is valid, and then feel free to cite whatever facts along these lines you want if they're true. Right? So you're responsible for having the geometric intuition to decide when can you make a transitivity argument, when can't you. So again, couple of landmines. Check it out. This vector V and this plane P are parallel. The plane P and this vector W are parallel, but V and W are not parallel. Right? So the idea that parallelness is transitive, not when there's a plane involved. Right? Now, when it's all vectors, yes. If you have three vectors, the first two are parallel, the second two are parallel, then yeah, the trio, they're all parallel, right? So it depends on what kind of objects you're talking about. So anyway, landmine, heads up. Don't accidentally, don't fail to visualize what you're dealing with and accidentally assume something's true because it looked good on the page, but forget to actually think about if it actually makes sense geometrically. Likewise, down here, just a quick observation of a landmine. P and Q are perpendicular, right? But then I can also talk about Q and this other plane R. So same Q, this other R. Well, Q and R are perpendicular. But notice P and R not perpendicular or parallel or nothing. They're just different. That make sense? Okay. All right. So careful. Okay, let's talk about parametrizing a plane. I got to tell you what I mean by that first. Keep in mind, we've talked about parametric curves. We've talked about parametrizing curves. The idea is position as a function of time is the way we think about it, but just to be more fair, parameterization of a curve, position as a function of one parameter. If we want to parameterize something different, in this case a plane, how would we parameterize a plane? I need position as a function of, one parameter is not going to cut it, right? If I have position as a function of one parameter, it's going to make a curve. That's what parametric curves are. I need to make a plane. A plane is a surface. It's kind of two-dimensional, and I'm going to make the pitch here that two parameters will account for that. The fact that I have a two-dimensional plane, we will be able to generate all those points. Keep in mind, a parameterization is a point generator. We're going to be able to generate all these points with two parameters as follows. Here we go. Let's see here. I want to generate this point x in the plane. Let's assume that I'm given a point in the plane already. That was a bad color choice. Let me redo that. I'm going to use orange. Let's assume that I am given a vector v parallel to the plane and a vector w parallel to the plane. Now all together, right? If I have an a and if I have a v and a w, that characterizes this plane. And I can use that information to generate x as follows. I just need to take my v vector and I need to scale it appropriately. I need to be able to move in the direction of the v vector by some amount. And then furthermore, this w vector, I need to be able to scale it. I need to talk about moving parallel to w by some amount. And now geometric appeal again. If I have a starting point in the plane and I want to be able to get to elsewhere in the plane, I can always do that by going an appropriate distance in the one direction followed by an appropriate distance in the other direction. As long as v and w are not themselves parallel or 0 or something silly like that. Everybody buy that so far? Okay, so I claim that this is a parameterization. I claim this gives me position as a function of two parameters. And you can even see the two parameters. Let me get rid of all this mess. The two parameters are these scalars, s and t. How much do you have to scale v? How much do you have to scale w? Right? And if you allow me complete control over those two parameters, s and t, then I can get from A to anywhere else in the plane, and this generates every point in the plane. Everybody good? All right. Notice it looks a lot like the parameterization of a line. In fact, you can almost kind of see this looks a lot like a parameterization for a line right there. So all we kind of did really is kind of add one extra term analogous to the one we already had. Okay, so let's parameterize this plane. Now again, let's presume that we're given 3 points, A, B, and C. And how are we going to go about parameterizing? Well, let's see. What do we need if I want to parameterize? If I want to parameterize, apparently I'm going to need a point in the plane, and I'm going to need two vectors parallel to the plane. That's what you have to have in order to use that parameterization formula. Okay, well, do I have a point in the plane? Where am I going to find a point in this plane? Oh, sweet, I have 3 of them. Pick one, it doesn't even matter. I like this A here because it has low numbers and a 0. All right, it's easier to work with, perhaps. I like easy numbers. Right? So arbitrarily, it doesn't matter, but I'm going to pick that one. And now I also need 2 vectors parallel to the plane. And again, I'm just going to do this pairwise subtraction trick. Right? I'm subtracting like so. Gives me 2 vectors parallel to the plane. And then all together, here's your parameterization, copying from our formula above. That parameterizes this plane. Everybody good? All right. Distance problems. Again, there's a bunch of different of these kinds of questions. I suppose it wouldn't be a bad idea to remember some of these formulas, but again, more important than that, remember where the formulas come from. I personally cannot remember facts very well, but I remember ideas really well. Right? And so make sure to remember the sort of the strategic insight that is going to make this formula work. That little cleverness, right? If you get the joke, as it were, right? That's easy to remember. That's the fun part, right? So try to make sure to understand the strategic insight, and then the formula is just kind of a matter of writing it down. Okay, so here we go. Suppose I have a point and a line, and I want to find this distance from the point to the line. How would I find that distance? Now keep in mind, if I know the line, I must know various bits of information about the line. I must know, for example, at least one point in that line, and I must know the direction that the line is pointing. Right. Okay, so with all that given, now again, it's kind of a puzzle. How am I going to use what I have to relate it to what I want? I have the point and this other point in that direction vector. I want this distance. And again, different ways you can kind of, strategize and make this work. I'm going to make the clever observation that if I view the distance as being the magnitude of a vector, I can relate that vector to that vector, which is just an easy subtraction, and this vector, which is just a projection. Right? So from the givens, I can effortlessly compute W. I can, all right, there's a little bit of, I'm going to have to write some things down, a dot product, blah, blah, blah. But I can, without too much trouble, write down the projection, and this orange vector I'm interested in is clearly their difference. So notice the picture was extremely helpful. The picture is the thing that allowed me to sort of see, that plus that equals that. It just looks like a vector sum, and then that leads to ultimately to the formula. Everybody happy? I see we're out of time, so we'll call it there. Nice ending point there at the bottom of the page. Y'all have a good one. See you Friday.